这边还是这边？OK OK，那可以。哇，使用is 725。一，天呐，啥呀？天，OK，嗯， Um, okay. Thank you everyone for coming to my talk either in person or on the internet. So this is the fifth lecture on entanglement bootstrap. So we have been talking about gap version of entanglement bootstrap, and there is a lecture for gapless version. Now this is about the um, gapped version. But whenever I say gapped version, I actually didn't really justify uh, why I'm calling this as a gap state. So the assumptions are about entanglement and edge law, but we didn't really make assumptions on the Hamiltonian, whether it's really a ground state of the Hamiltonian. The only thing I mentioned was that the physical motivation was from ground state of gap Hamiltonian, because usually those states have entanglement edge law. But now let me talk about some more deeper connections to phases of matter in a more precise way. In particular, we will make connections to the another very useful idea, very important idea of classifying phase of matter called finite depth local unitary. So if you have a gap state, you evolve this by a finite depth local unitary, you get another state. You will be in the same phase of matters, the same gap phase. That idea has been there for maybe 20 years. At least it dates back to the work by Hastings and Bowen, which show that if you perturb the Hamiltonian, deform the Hamiltonian, then the ground state will evolve by a finite depth local unitary up to some tail, some correction. Yeah, I'll explain this term. Maybe this is only familiar to a small subset of the audience. Yeah, but on the other hand, entanglement bootstrap gives some natural point of view of two phases of matter. The phase of matter equivalence according to space uniformity. So the space is uniform. If the space is uniform, then we say the two are the same phase of matter. So like uh, this this places has an axiom satisfied. Right. So alpha both alpha and beta satisfy the two axioms A0 and A1. But how about we will try to join them, and there's a wall separating them. So suppose the wall is transparent, we will say they are the same phase. So alpha is equivalent to beta if they are separated by a transparent wall. The wall is transparent. Okay, so this is the space view, this is time view. Are they really the same thing? That's one topic I'm going to talk about. And another thing to mention is that where to find those state satisfied axioms, or if you wish, you can call them entanglement bootstrap state. Where do we find them? So if we have a phase diagram, this is the phase diagram. The diagram with the 1, 2, 3, 4, a different so-called different phases of matter, and should we expect that every state within the gap phase is an entanglement bootstrap state? So one argument is that that should not be always the case, but maybe there are special points in the phase that satisfy the axiom. But if you deform away from it, it will no longer be a fixed point. It's approximately fixed point. You have errors to the axiom, and the axiom, we will hope that the errors to the axiom will go away when we zoom out to large length scales. That's true in most of the numerical tests, but people can come up with this very special state. Well, if I couldn't prove how special they are, but there are special states you can explicitly construct that violate axiom A1 to a length scale. And nonetheless, you can remove the correction for all known such examples. Those examples are called states with a spurious contribution to entanglement entropy. And for all such examples, you can remove the spurious contribution by some finite depth local unit. I'll explain this later. But the idea is that the correct version, the correct way to understand the relevance of phase of matter to an entanglement bootstrap is to assume that some, at least exact, well, there exists there exists assumption or conjecture. Well, let me say this is an assumption. Assume at least one state in phase is an entanglement bootstrap state. Yeah. So if we take this assumption, then I'm going to show that the entanglement bootstrap can indeed tell you a lot of valuable information on classifying phase of matter. Well, there are actually different perspectives. One is to work with this original version with the reference state has A0 and A1, and show that once you have this one entanglement bootstrap in your phase, whatever you extract from the state really tell you about the phase of matter. So you don't get a spurious contribution because axiom excludes it. If you really have this clean and nice state, you know a lot. That's one approach. And the second approach is to replace A1 by a circuit manifestly circuit invariant version, which you need a little bit more drawing. I will show you at some point in the lecture. And this is a work by Daniel Renat, Alexia Kitov, Milo Moses, and Ada King. They have been working on this for more than 1 year, maybe 2 years. And they have been telling me how this works. I'm learning, but I'll give a brief overview. And there are some other progress on showing if to turn in the space picture into a time picture, whether the two states separated by a transparent domain wall will be converted to each other by finite depth circuit. I'm currently working with the grad students in Caltech, in the that's the overview of today's topic. So first, by the way, there's also some question by Zhihao, that whether the anion defined from a Hamiltonian in terms of excitations of the Hamiltonian will be the axiom defined in terms of information convex set. Since I'm talking about Hamiltonian today, I find the opportunity to answer this question in slightly more detail. Okay. I think 10 to 15 minutes into the talk, I will get a chance to answer this question, and also talk about the circuit, so-called circuit depth, the circuit, how to build unitary circuit, how to find the unitary circuit to create the anions, and whether the depth is a shallow depth circuit, a linear depth increase with the separation of the anion. Okay, and now let me start reviewing things about Hamiltonian. Hamiltonian. Local Hamiltonian. Well, the Hamiltonian is a sum of terms, and by local Hamiltonian, we mean geometrical local. So each term is supported on a geometrical local set of spins on the lattice. So the range is bounded, and then your L is order 1. And as your system becomes larger and larger, this length order 1 is still order 1. So it doesn't increase with the system size. And for the study of topological order, we don't require any symmetry. So we don't no global symmetry. And no translation. Yeah, so it's okay to add perturbation. So h prime equal to h plus delta h. As long as the Hamiltonian perturbation is small. So suppose you have a gap. The original Hamiltonian is a gap. The important claim is that if H is a gap, and you have a Hamiltonian path from, well, let's see, H0, and connect it to H1. In the middle, you have H of T. Depend on some evolution parameter. So if this is a gap all the time, then you have finite depth local unitary T. Such that the ground state of the first one is some finite depth local unitary acting on the ground state of another Hamiltonian. And what is the finite depth circuit? Now I need to explain that. I think this is a and later on this will become important in the classification of short range entangled state, long range entangled state by 辜正成辜的纲文 in 2011 or maybe the audience knows better than me. Okay, so what is the finite depth circuit? The definition is the product of a unitary acting on, well, what is the depth? By the depth means the number of layers. So imagine you have some system. For convenience, I draw one dimension, and you have set of qubits. So the first side, the second side, third side, and so on. And we do a geometrically local unitary. Geometrically local. In this lattice, I draw like two sides. But yeah, locality is important. I'm drawing this in 1D locality, but for 2-dimension, you imagine something acting within a bounded radius ball. So this gate, the first gate is a unitary. This one is a unitary acting on 1 and 2, so I call it U1, 2. Yeah, the Hilbert space of 1 and 2 is a small Hilbert space, and you pick a unitary from the unitary acting on that Hilbert space. And this one acting on 3 and 4 can be applied in parallel, and so on. So this is we will call this the first this is the depth 1 circuit. Then you do another layer. This is called the second layer. And if you have both layers, this is a depth 2 circuit. You can convince you that because the support of this circuit and that one had overlap. If you pick a random arbitrary unitary, they may not commute. You cannot convert this into depth 1. You need multiple depth of circuit. So the finite depth. Oh well, many people complain about the word finite depth local unitary, because this is what some people prefer to say this is a shallow depth. or constant depth. Well, there are different names, but here the finite simply means the is a finite number that's independent of the system size. Here to see this one is a finite depth local unitary with a decaying tail. Yeah, so those gates may not be completely local. They may local up to some exponentially decay. Yeah, thing related to the Lieb-Robinson bound. That's a technical thing that I'm not going to say too much about today. Okay, so actually, how much of the blackboard should I use? Right here, here. Okay. Mm. Right. So now let's um talk more about the unitary. So if you have a Hamiltonian H0 and you find arbitrary unitary, you H1, H0, your dagger. Mm. For any unitary, finite depth or not, any unitary, then the spectrum will be the same. But however, if we look at an individual term and conjugate by this big unitary, uh, this will be, let me call it H theta. Usually this one will be much better. So it could, maybe this is the nearest neighbor Hamiltonian at the beginning, but after doing this very general unitary on the whole system, it could be like a term that couples to the first side and the 100 side away. And then the locality is gone. So that's why we don't, one reason that we don't want arbitrary unitary. So we want locality preserving. Such that H1 is local, will be local. Mm. By locality preserving, the most general locality preserving will be quantum cellular automata or QCA. Is a locality preserving unitary. Yeah, so why not classifying phase of matter up to QCA quantum cellular automata rather than finite depth circuit, right? Those two concepts are quite related but different. The QCA is broader than finite depth local unitary. Yeah, why not? Can someone does anyone want to answer this question? Why not use to say to classifying different phases? Like one can propose that one state it can be converted to another like a QCA, then they belong to the same phase. What's wrong with that, right? It turns out there are well, let's consider some state, some Hamiltonian is on a system of a torus. n-dimensional torus. Uh-huh. Yeah, exactly. Yeah, that's a great one. So Yizhou was saying that the simplest one is a detailed chain. In one dimension, it's a fermionic system. And in fermionic system, there is a non-trivial Z2 classified quantum cellular automaton that's the shift of Majorana in the Majorana basis. So it's half of a translation. Yeah, it turns out, yeah, that one can convert the K-type chain to a trivial phase. And this should be different on physical ground. Yeah, that's 1D. Right. So if for W is in the set of QCA. Yeah. So one thing you can say is that the spectrum are the same. So if this one has a one ground state, then but QCA is a unitary. It's a unitary on the entire system. Yeah, my definition will be that. Yeah, that's your definition is some automorphism of the operator algebra. Yeah. Yeah, so my definition would be some unitary on like maybe 1000 times 1000 lattice, but it only mess up the locality after 2 or 3 sites. Yeah, I can find such operators. But if we find such a unitary, then the spectrum are the same. If this one has a unique ground state, H0 has a unique ground state, and H1 also has a unique ground state. So you can argue this way that you shouldn't create a topological order with this because topological order should give you a degeneracy, right? That's roughly the idea. But then uh, you may get invertible phases. Invertible phases are defined to be a system protected by no symmetry, but that cannot be deformed into the trivial state. So no symmetry to no annual. First of all, no annual. Well, no topological order, no excitation, no non-trivial excitation that cannot be created locally, no annual or interesting excitation, topological excitation. But it is not finite depth local unitary equivalent to the product state.
So for the finite depth local unitary, so the HI tilde it is local, but it may not local at the original region, right? Is that
Yeah.
But for QCA, it's
Yeah,
still
it's a local near the original place.
Okay.
Yeah. Yeah, thank you. So for this, there are several examples. Also for when I wrote this, I assumed photonics, but you already gave a 1+1D photonic example. Yeah, that's the next example I'm going to give you. Well, some are really conjecture in the most precise sense. It's in literature for higher dimensional invertible states. Majorana translation. In higher dimension, there are well, this is a photonic photonic one. 3+1D vector 1. Yeah, so the state state of worker one is equivalent with the QCA to the product state. And there is a conjecture that the QCA is non-trivial. That's a conjecture. And I think there's a couple of examples, similar examples for 4+1D as well, some invertible state and similar story.
I have a question. When you say QCA preserve locality, does it mean that it preserve locality for all local operators,
Yeah.
whether or not they appear in the Hamiltonian?
Yeah. So for all local operators, yeah. Hereby when I talk about QCA, I mean a unitary that maps any operator to some local operator nearby, whether or not that's a term in the Hamiltonian. And I guess you do talk about another instance of QCA that preserve a symmetric subalgebra that's related, but it needs not to preserve every operator. That's the difference. Yeah, good. Right. So yeah, those examples are extremely interesting if we want to classify in face of matter, because
For those examples, it's a QCA and finite depth local unitary. It's very difficult to imagine such a thing. Do you have what allows it to preserve locality for every single local operator, but not but that it is not a finite depth local unitary? Can you give us a sense of what it looks like?
Yeah. So yeah, let me give you a sense of why this set is larger. I can do this in 1D. 1D. In 1D, you imagine you have a system on a circle, for example. Well, we can talk about infinite system, but I prefer finite region. The definition would be slightly more tricky, but like at least according to Hastings and Friedman, there's a way to make this rigorous. I'm allowed to talk about a torus. A circle. Let's say a circle spin chain in 1D. A non-trivial QCA would be a translation. Translation to x to x plus 1. Yeah, that one is the locality preserving because it brings the operator on set I to set I plus 1. Yeah, it turns out it's not. Oh, okay. Good. The problem is the middle. So if you are in the continuum, I think there shouldn't be any problem. But the problem is this is a discrete system. Yeah. Therefore, yeah. So you have this side down here, right? So what I mean is that you can map this side to that side, but what do we mean by the middle? Two sides is not good. Oh, yeah, then that's okay. Yeah. So in fact, the more general thing in 1+1D, so 1+1D, there is a famous GNVW index. Yeah, if you search those four letters, you can find some index for quantum cellular automata in 1 dimension. I think their result is nice in the sense that they didn't even need to assume translation symmetry. Yeah, it's more robust than translation system. But for translation system, I can say, oh, and one example is translation, but actually you don't need translation symmetry. All right. No. Mm. Okay. Next I will make some comment on like how the finite depth circuit can violate the axiom and why we have different approaches to deal with this problem. Why the original version is okay and why the other option seems effective as well. And and then I want to talk about string operators, like anion string operators, and how those are related to circuits. Reflection is not, because you take the origin, right? But an operator left to the origin by some distance will be reflected to the other side. So there's some big distance. Yeah. But the locality preserving is saying you map an operator to the neighborhood. It is stronger than that. Yeah. Right. I guess I should explain what locality preserving is the stronger one. So, okay. So if we take a unitary from finite depth local unitary, that means you have u of t such that u of 0 is identity and u of 1 is u. Yeah, therefore, you can continuously deform the h to the other one. Let's say this is h0, h1, ht is u of t, h0 is the dagger. Yeah. So you have a continuously tuned parameter from 0 to 1 such that h of t has the same, well, it is another local Hamiltonian where it has the same spectrum. In particular, it remains gapped all the time. So you deform a gap state to another gap Hamiltonian, and the ground state are deformed as well. Now suppose we have h1 equal to a sum of well, projectors. Well, suppose each projector is on a single side. For instance, P of I is a single side poly. Let's see, P of I minus sign. Then you have ground state of this Hamiltonian would be I don't want to minus sign 0. Yeah. And then if you do this finite depth circuit, you may get a more some other Hamiltonian. It will be in the same phase. Finite depth local unitary acting on 0 will be in the same phase. And let's now check the axiom. So A0 and A1. So first on a state zero. So suppose you have a two-dimensional system with all 0, the product state of all 0. yeah, something like that. Then it's pure state everywhere. So when you check the axiom, it gives you a 0. C and D as DC plus SD minus SD will be 0 plus 0 minus 0 is 0. Yeah, everything looks good. Again, it's 0 plus 0 minus 0 and 0 is 0. So it's a good reference state. It's somewhat trivial, and if you compute the information convex set, you always get the same state, and the state is pure. Yeah. But how about this state, right? The one acting by some finite depth unitary. Yeah. You have so many choices of finite depth unitary. Can we on this new state, can we still check the axiom? It turns out axiom A0 is okay. And A1, you can find a counter example. I'll show you one counter example. Can be violated. So I'll talk about one of the early examples, or Bravi's counter example. Okay, so it's the following. So A, B, and C. Yeah. I wanted to say that the axiom needs to be violated. The equivalent statement would be the topological entanglement entropy is non-zero. So let me define the topological entanglement entropy. I'm defining the gamma, the topological entanglement entropy in the G-type Pascal partition. It's called KT G-type Pascal is SCD plus SCC minus SD, okay, plus SCC. All right. So on the all zero the product state, this will be 0. I'll give you 0 for the product state. But I'm going to make some state following Bravi's construction that give you some other number for this partition. You Bravi testing on 0. So the circuit is actually very simple. It's putting some 1D state on top of the 2D. This is a spin chain. The spin chain on the red circle, and put the circle into a zigzag. It's the UN, all the UN sides are lying outside ABC, and all the outsides are lying within A, B, and C. And the state we put on the spin chain is a so-called cluster state. Yeah, that's a one-dimensional STT protected by Z2 times Z2. That's a detail. But what's important is the fact that if you have any subset of the half chain or the even side, if you take any strict subset, your subset, you find that the entropy is just you can get the entanglement entropy by simply counting the number of sides. But if you have all the sides in it, there's a you need to minus log 2, so the entropy is actually smaller than what you predict by looking at individual qubits.
This chain is just put on top. It doesn't entangle with anything. Just put this chain around it.
Yeah, that's right.
Okay.
So the contribution of a SAB, right? Yeah, when we put on top, we need to count the three qubits as a part of A. So right. So the contribution of the cluster state in red color to those terms will be what this is the additional contribution. Well, yeah, I think actually that's all the contribution. So it's the number of sites in AD. So let me call it data n AD. The number of sites 1, 2, 3. So 1, 2, 3. I think 3 of them in A, 3, in B. Yeah. Yeah. Okay. Let me say this is 6. And this contribution is the NBC, the number of sites in BC. Or it's actually 6. And A equal to 6. And A is 3. And B is 3. And C is 3. How about the entropy on ADC? So you have all the sides of the half chain. It turns out because there is a Z2 symmetry acting on here, which can be deformed away. The contribution is a 9 minus 1. So it's NADC minus 1. Therefore, you don't get 0. Instead, you get gamma equal to something. Yeah. Let me just here.
So I got lost. SAB has 6 sides in it, but okay, because you put one side outside of this one.
Yes. Minus 1. Yeah. I think this is the one. Yeah. 1 times log 2. Yeah, so it's something. Wow. But note that if we only have this one, somewhere we have violations of the axiom. So gamma for some partition is 1 log 2. But if you move the partition away from the circuit, you get 0. It's like this figure. So for some partition, they give you log 2. So for another partition, you get 0. And therefore the axiom, entanglement bootstrap axiom, must be violated somewhere. Yeah, either here, there, somewhere. Yeah. The axiom cannot be satisfied everywhere. Because under axiom, we can show the invariance. We can deform the region smoothly without changing the gamma, the subleading term of the area law. So in other words, this example, rather than say this is a series in terms of a correction to the subleading term by the same amount everywhere, it's a correction that makes the value not uniform. That's always the case. So it usually can be detected, so it's not that serious in some sense, but it's something people need to worry about if they have a real system and only have a limited ability to check the entanglement entropy. Maybe they only compute this in some places, and it takes a lot of effort to compute the second one, and we need to worry about it. All right. So okay. Now take a detour to talk about string operator and anion. String operator, anion string. So first of all, the anions, whenever we have a solvable model, we have ways to define anions as excitation. And A equal to excitation, point excitation. Mod something you can create locally, like a local operation. So that doesn't really make sense in entanglement bootstrap. I am going to explain why disagree with the other definition. Okay, according to information convex set, this one, annulus give you a simplex, and this labels will be set of row A on the annulus, the set is extreme point. And from those extreme points, you can define a anion are extreme point. Why are they the same thing? First of all, let's take a reference state. And try to apply any local operator. So consider a local operator on the region. Let's call it C. So any O of C acting on the, well, I guess you're to be convenient. Let me just verify this state. We assume some pure reference state psi acting on psi. It turns out the first thing we can say is that it is equal to some constant times unitary on BC and acting on psi. And this follows from axiom A0. Why is that? The reason is that, well, I need to tell you what is B. So B is the buffer that separates C from the rest of the system. It's like you have a local operator acting on psi. It didn't really affect places far away from it. Psi is the reference state, so it locally satisfies A0. A0 is true on BC. So which tells you that SBC plus SC is SB. Which tells you, yeah, let me sketch the proof. The proof sketch is that because we have A0 centered at C, the entropy conditions code which implies that the state must be a product in something. So psi is psi, yeah, the rest is A, then let's call it A, B, L, and psi, B, R of and C. For some decomposition of the Hilbert space, for Hilbert space, H and B decomposed into HBL, hence HBR, and direct sum with some other things we don't really care. But the important thing is that BL and BR are not subsystems. So if we take it literally and thought BL and BR are subsystems, then we will be able to draw a cut in B, such that the state is disentangled. The interior and the outside will be completely in a product state. But that's not true because in the Tory code and some examples, you know that no matter how you cut the system, you have area law, which is a non-zero. But what is that here is slightly more subtle. It's saying within some more abstract decomposition of the Hilbert space, you can separate a Hilbert space called HBL and another Hilbert space called HBR. Yeah. But the way of touching the region, then you can write a tensor. Yeah.
As in, this cutting does not respect locality or?
Right, it does not respect locality. So you can imagine you have some unitary acting on the entire region B, which may not be a finite depth circuit.
B left is not some local thing. It might include many strings in B.
Yeah. Yeah. But this is already powerful enough to justify this. So any local operator will be some operator supported in a slightly thickened region, but it still preserves the locality. In particular, because the unitary, the operator behaves like a unitary on BC. That means if you take an annulus surrounding this region, take this annulus and try to ask whether the operation affects the density matrix on the annulus. It turns out it doesn't. So in other words, suppose you are originally you are at this extreme point, and you ask whether you act a local operator give you another extreme point. The answer is impossible.
Where is the local operator?
The local operator is in C.
Oh.
Yeah, this local operator. So yeah, the conclusion will be OC can swap any extreme point. Yeah, so the local operator doesn't work.
For a given size of C, can you somehow bound B with a finite known diameter or some size?
Oh yeah, the diameter of B, so the width, right? The width of B. The width of B is controlled by the length scale that you set it by axiom A0.
Okay.
Yeah. So remember we have some length scale. Yeah, kind of the correlation. Yeah. Let me just say the correlation.
I see.
It can be as big as you wish, right? Because it is only at very small scales that it starts to be bad. Yeah. But as soon as I see A0, A1 emerge at some scale, I can be as big as I wish. Then B can be huge.
B can be huge. Sorry. I thought we have the following. Maybe I misunderstood something. But first we have some length scale that A0 and A1 emerges. And then we talk about information convex set on larger length scale.
Yes.
Yeah.
So the thickness of B can be very large.
And
A0 and A1 works.
Yeah. But typically it's just a 2 or 3 lattice spacing of the coarse grain lattice. So it's relatively small comparing to the thickness of this and so on.
A thickness of
the annulus. The annulus we pick for computing the information convex set. Yeah.
It's bounded by the annulus. Okay. So as you're saying that as long as B is smaller than the annulus, then there's no way this OC can change the extreme points.
Say it again. As long as
B is bounded by this, the thickness of B is bounded by the actual annulus where you're computing the information convex, then this local operator, this OC, cannot do anything.
Right, it's like C is here, and we find the annulus away from C by enough distance. Yeah, there's enough distance.
Oh, okay, I see.
Then it's okay. It's like the operator acting deep in the hole won't
Okay, I see.
affect the state on the annulus. And therefore, if you want to create anion, you need to try harder. You'd better not use local operation.
As in, you're trying to make locality a little bit looser. It's not strictly local, but as long as it is somewhat separated from the annulus, you won't change the you won't change the extremal.
That's right. So in the solvable models, if you have a Turing code, we can say one lattice set and two lattice sets. But if we only know the correlation length, we are not in the exactly solvable model. It makes more sense to talk about one correlation length, two correlation length. Yeah.
So this statement is that like a local operator acting on a reference state is like equal to some local unitary acting on a reference state. And then how does this imply that local operator does not swap extreme point?
Okay, because of the following. So you have alpha is the lemma. If you have alpha AB and beta AB two state. So first, if you have a beta equal to essentially we have C anyway, so you B of alpha, then the reduced density matrix of them on A will be the same. Alpha A will be beta reduced to A. Yeah, unitary doesn't change the reduced density matrix on the complement. But in fact, the other way also if alpha A equals to beta A, then there exists a unitary B such that beta is UB times alpha. Yeah. So actually this is pretty useful. I'm going to use it shortly. Sorry. Yeah, this is holds for the pure state.
But does this only imply that when you're acting on unitary on a reference state and the information convex set are like the same, but can it induce a non-trivial
for point like operator, it's impossible to create change the extreme point. Yeah, so more generally, any operator that are separated from the annulus by some distance. Yeah, for any such operator, local or not, it cannot change the extreme point. So let's talk about operator that touches the annulus. So let's talk about the operator. So to make some non-trivial influence on the annulus, we'd better came up with an operator that supported somewhere. Yeah, here. And by this lemma, yeah, this argument also applies to the string operator. So first we know that. So if we apply O to the no, this is C. Yeah, let's call it C. So C acting on the reference state, purified the reference state, is some constant times some unitary on the thickening of the string. Let's call it C plus acting on that. Yeah, thicken a little bit. Maybe I want to use a different color. It's thickened by some distance, but still it's like a string operator. Yeah. In other words, we can always consider unitary string operator. As long as we are only interested in some operator acting on the ground state, we can replace the operator by a unitary one. So it's enough to talk about unitary. The next thing I want to say is that the unitary can be are deformable. Any operators are deformable. And to illustrate how this works, it's sufficient if I consider a sphere. And suppose you have some string operator that creates a pair of a pair of objects on the North Pole and South Pole. And detecting annulus, I try to make it as large as possible. So let me pick the annulus to be this one. One of them is a vacuum, one another is A. And suppose after applying the string operator, we get another string point. So from side, the A is this unitary acting on cell 1. So the reference state cell 1 acting on this string operator, we get cell of A. If so, we can. I'm going to argue that the string can be deformed. So side A, try the propagation. Side A will be another string. So yeah, let me call this as a unitary on theta. So this line is theta. But I want to say that the string can be deformed. So the deformed one will be some other string of theta on theta prime on theta prime acting on that one. So I deform So why can we deform the string? So it's actually it's related to this lemma, right? So let me show you this again. So it's on a bipartite pure state, if the two states are the same on some region, then there must be a string operator supported on the complement. So in order to apply that, the situation is that we want to look at the complement of this and tell whether the two states are the same. And obviously on the information convex set, the information convex set is locally like a vacuum, but globally they are not. Nonetheless, as long as we trace off any part of the annulus, we end up with a unique state. Yeah, this is the reference state on it.
Sorry, why string?
Why string?
Why is it that it would be a string operator?
Why is that a string operator?
Yes.
Oh, good. Actually, I don't need yeah, could assume something more general. So any operator. Let's try that. Any operator passes through the annulus. Could be like this, right? And suppose it create excitation only around here and give you some element in the information convex set. Yeah, we can just assume that. So let me so call this as C. The support is C, then still it's unitary acting on C plus. And now suppose going from there to here, suppose the new state of A reduced to some real A in the information convex set. Then we can apply this lemma to show that the operator can be supported on a string. Yeah, how about that? I think that's better. And thank you for that. So that beta will not be a string, but some better version of the operator supported on beta. Now we replace the support of a beta to a string like support. String that that passes through. Yeah, it's a string and it's deformable. Yeah. Yeah, the proof is by the lemma. On the annulus with a string removed minus a string. So this is the string, so minus the string. Yeah, this is the disk. The disk. If you wish, the disk that almost complete the big annulus. We have the reference state. So the row 1 and row A are the same. A reduced to this disk, give it a name, call it D. Reduced to D equal to the 1 reduced to D. Therefore, there exists a unitary on the complement on the sphere minus the disk. That's that. The unitary on the sphere minus the disk acting on set 1 is set A. But now we see the trick. The trick is that what is the sphere minus the disk? It could be the complement to any deformed string. You can or string going from up to down. Yeah, you can deform it in any topological way. The complement will be a disk, so you show that there's always such a string operator.
So it doesn't have. So this is the way to see that one-dimensional object is enough.
Oh yeah, exactly.
Instead of being fatal.
Yeah. So you can try to enlarge the complement as much as possible. That's why. On the other hand, I want to prove the following. So you suppose you have a deformable finite depth circuit. So here is a theorem on the other direction. It's like if suppose we have a deformable string acting on psi equal to let's see, the first one, the second one acting on psi. Then it passes through the annulus. So this is your annulus. This is your first choice of string operator, beta 1. This is your second choice, beta 2. if the string can deform on the reference state, then the state is defined will reduce to some give you an element uh, on I guess it's fairly straightforward in the sense that well if we have a unity here, we want to check an element is in the information convex set or not. We only need to check it locally looks like the reference data on the beginning of the angular. But if the string is here, which part is hard to check is this disk. So the disk touches this string, then we are not sure. But because of this, we can always deform the string from here to the somewhere far away, so we can avoid the string from touching this any ball. Yeah, so we have that. Right here. Avoid string. And there is a stronger statement. So this is the first thing we show. And second is that if in addition the string operator is a constant depth circuit, finite depth local unity. Then the extreme point is abelian. Then Q of A. Doesn't guarantee that's an extreme point. That's right. Yeah, that's right. Yeah, we can create a non-extreme point using some unity. And the depth will be the depth will not be constant depth. Yeah, actually, I felt like I was somewhat left behind. So maybe let me just state the result and comment on one or two words, and I'll move on and to talk about state of matter. Okay, the result we have is that I'm not going to explain everything, but if A is abelian, we have finite depth local unity, and vice versa. If you have a deformable finite depth local unity, it must create some abelians that could be the trivial one, could be non-trivial one, but it can only create a abelian angle if A is non-abelian. You have a linear bound, so take a linear bound circuit. Linear depth, sorry, linear depth unitary. In fact, this could be a sequential circuit. Sequential unitary is enough. What is the sequential unity? It's a linear depth circuit that goes like this. It's like you try to move the anion to create an anion pair and move one of the anion to the right by 1 unit and then move to the right by 1 unit. Those operations don't commute with each other. So you need to do one step and then the next. Yeah, that's a claim. But what's the intuition? I mean, although I ran out of time talking about the proof, but the intuition is kind of simple. How to create a pair of abelian anions to separate the far apart? The trick is that you can create a anion pair. Anion pair. Here. You have a separate unitary that creates a bar, a bar. But then the next step, you try to annihilate the anion. So annihilate this pair, annihilate that pair, and then you left with a and then a bar. So a large enough length scale is a depth 2 circuit. But what's wrong if you try to do the same thing for non-abelian anion? It turns out the non-trivial part of non-abelian anions is that if you have separate string operators to create a bar, on the other end would be a bar and a. Then let's try to annihilate them. So let's try to see how they talk to each other, and to do so we can draw a large annulus. So if A is non-abelian, that means A times a bar could be one, could be at least one other thing. Yeah, at least one other charge. That means on the annulus you have the both 1 and B and some other things. Oh, they all appear on the annulus at the same time. You have a non-extreme point. And the fact that you have a non-extreme point on the annulus, that means you create some non-trivial mutual information between part of the annulus. So if I draw this annulus into this way, just to give enough distance to partition this burden, so A, B, and C, you can ask about the mutual information between the two, the A and C. Mutual information between A and C for any extreme point will be 0. However, if your state is some probability of zero 1 plus some non-zero probability of zero B, then this will be greater than 0. Yeah, so you have some mutual information created, and to generate such mutual information, it's hard. So you cannot just put constant depth circuit here and constant depth circuit there to create mutual information between regions separated by distance. So, but okay, I need to admit that in this figure, I draw a very thin annulus that may not be sound hard, but if the annulus can be thickened, yeah, I can draw a thicker annulus to separate A and C by larger distance, and then the circuit depth will be lower bounded by that distance. It could be linear, linear with the system size. Yeah. Okay, now let me go back to the story, the main story that how to relate the space and time. I believe we have some familiarity with the space point of view. It's like if the wall is transparent, then we have perfect reference state that covers both A and B. We should treat them at the same phase. At least at the intuitive level, we should believe that, and there are many supporting evidence. For example, well, in particular, A1, axiom A1 is like a uniformity. Remember that when we try to deform some region from here to there, deform this annulus, the elementary step will be adding some bound on the local region, and of course you can remove pieces and so on. So you move these things around, and for the topological entanglement entropy, gamma A, B, and C, you can deform the region to A prime, B prime, and C prime. And similarly for the modular commutator, which computes this computes the total quantum dimension, the sum of A squared. And for the modular commutator, the same thing. You can try to argue that it can be deformed smoothly. A prime, B prime, C prime, which compute the chiral central charge. Yeah. So yeah, that's some sense of homogeneity, and we can deform the annulus as well. Well, not only annulus, any information convex set on even for inverse region. And let me be fancy, enjoy inverse region. You can deform this from here to there. Omega theta. The information convex set of omega is isomorphic to that of omega theta, as long as we can deform omega to omega prime. Yeah, so that there are plenty of evidence that the space is homogeneous by the axiom. So there's a space view of quantum basis of matter. But on the other hand, there's a sort of an idea or question. About phases of matter, space versus time. Yeah, what can we say? And another question, question 1, question 2. On the circuit invariant. Yeah, because A0 can be broken. It's not invariant. And actually, there is a third question as well. The third question would be, sorry, thank you. Yeah, great. A1 is not invariant. A0 is invariant. The third question is whether the finite depth local unitary, the traditional idea or not traditional, but it has been there for quite some time, is itself is enough or not. Yeah. Actually, I will try to cover some answer to all of them. But let me start with simplest one. Actually, this one. So usually we say we think this is enough, but in detail there's some subtlety. So for example, when is this viewpoint work? When is finance that local unitary a good idea? Yeah, for many reasons, this is a good idea, excellent idea. For example, you can ask whether this is a finite depth local unitary equivalent to the Torah code ground state, which is written as a superposition of loops. Yeah, the answer is no, you cannot. You cannot. Yeah, so they are not equivalent. This can be rigorously proved. There are multiple different ways to prove this. I won't tell you which one, but that's an exercise. It's easy to prove they are different under finite depth unitary. So indeed, it's helpful for us to distinguish different phases of matter. But for some other, so if we take this literally and try to do it topologically non-trivial manifolds, there is a problem. So one counter example would be a counter example of a finite depth local unitary classification would be torus with a torus code. Yeah, we all like torus code, so I'm going to say torus code and torus code and a torus code with a defect. So you have a EM exchange defect passing through the torus. So yeah, so this is the EM exchange defect, and if you move E particle around, it will become M. So they are different. But if you have a local Hamiltonian, this is a Hamiltonian 0, Hamiltonian 1. You can ask whether H1 is the finite depth local unitary equivalent to H0. And the answer is no. So clearly, the answer is no, because the ground state degeneracy of H1 is 2. But the ground state degeneracy of a Torah code with no defect is 4. Yeah, so there's no way to convert them to each other by finite depth unitary. But do we want to call them as different phases of matter? The answer is we don't want to call them different phases of matter. We want to say that they are the same phase of matter, but one with a defect. Yeah. Therefore, we need to refine this one. So the answer for question 3 would be naively using finite depth local unitary is not enough. And we want to refine them by saying like alpha reduced to a ball is finite depth local unitary equivalent to beta on a ball. Yeah, that's a equivalent of phase classifying. Yeah, we want to classify and gap the phase on a ball. But even with this modification, it's it's still not enough. I'm going to give another counter example. If we don't require any entanglement bootstrap technique or anything, we need to argue that, oh, we have a good lattice model in order to do that. And let me give you an example, some example of bad lattice model. So yeah, it's simple. It's like alpha. Well, alpha is a alpha on a lattice on a, let's say 100 by 100 lattice, which is like a ball. A beta is again on a 100 by 100 lattice. Again, suppose this is the third code. But now for beta, I want a third code with a defect endpoint within it. Yeah. And this is the EM exchange defect. With similar argument as this one, is not exactly the same thing, but the defect is a billing in concrete sense, and you can prove similar statement that if you want to have a defect in here, you better have create this by a linear depth circuit. There's no cheaper way to create this. Because those two states are not up to a final depth circuit, so we need to be very careful. So we need two modifications of this naive idea. And the answer is no. And then for the yeah, right. So the defect endpoint carries some quantum dimension, and if you build 12 of them, you get just multiple different results. Yeah, that's why that applies. Yeah, it's the second case. So not only that, we need to talk about state on the ball. We need to have some uniformity condition, homogeneity, uniform on the disk, and to avoid defects. Yeah. And what might be the right homogeneity condition? If you have if you're lucky, you have a translation inversion model. I think that should be sufficient. That's sufficient maybe. But even in that case, you may worry whether this one and the rotated version of your state belong to the same phase. But in entanglement bootstrap, we have some natural candidate of a phase homogeneity, and therefore, maybe we can fix this idea and have a better version of the idea based on entanglement bootstrap. So then this back to to combine the idea of space and time. This seems to be necessary. Okay, based on that, I will pose some natural questions and claim that we yeah, I'll write a natural question and claim that we will almost have a solution where kind of yeah, almost have this, and we are kind of getting down some concrete version to um, convert space to time and time to space. So here is a natural question to ask. So let me see a problem. The natural problem to consider would be if you have a state. This is the alpha, this is beta. So both of them are supported on the ball. I'm using this idea. And suppose there are two directions of the question. So suppose alpha and beta in space are equivalent to beta in space. And namely, we have a transparent wall. Then we can find the finite depth circuit. And then alpha on the ball will be finite depth local unitary equivalent to beta. And the other direction will be if alpha.
Beta also on the ball, right?
Thank you. Yeah. If alpha is a finite depth local unitary equivalent to beta, then we can it's possible. We can have a transparent domain one. Yeah, at this moment, I think yeah, student and I almost have the part A. For part B, we are thinking about it. I think there's some idea to fix it. But due to the time limit, let me just get one step related to point A. I want to create replace some cells of beta with alpha. So suppose you have a beta on a ball. I want to be able to create a state with the beta almost everywhere. Okay, but with some cells of alpha. The alpha on a 0 cell. Yeah, it's convenient if I have some colors. So alpha is colored this way. To go from here to there, I need to put the toolbox of entanglement bootstrap. It turns out the useful idea is related to immersion. Right. So how do I do that? How do we do? It turns out we first create some holes. So in beta we create a hole by tracing out some region to leave out some space. Now we have a hole, and this part are filled with quantum state, but this part is traced out. But then remember that we can deform the region around. Like this edge of the hole can be deformed either, well, we can deform this outside, right? We just remove more of this images. That's one direction. But what's useful here turns out to be the other direction. I'm not going to deform the boundary this way, but deform this inside. So you see that there's no much space. So with the tool of immerse the region, you can construct yeah. I think yeah, this part extend this boundary to this part. That immerse the disk. You add the immerse disk to the original region and make this bigger and bigger. We can pull out some pieces of alpha back to here. So yeah, so the step into that, we create some small holes around here and pull out some space from alpha and fill in here. So you have local pieces of alpha on the background of beta. And in particular, if alpha is the vacuum, suppose alpha is the vacuum, then this will be a gap the boundary. Then we will be able to have a gap the boundary everywhere. Yeah, so we created gap the boundary with the vacuum in the hole. If we have a string net or something, if we know there is a gap the boundary, we can do that. But more generally, we created a state with zero cells replaced by alpha. It turns out this not only works for 0 cells, we can replace the one cell, and then 2 cells. And we can turn the state alpha to beta by 3 steps. Step 3 quantum channels. And therefore, yeah, we justify this B part. So the direction that we turn as space to time. Yeah, from time to space, we'll yeah. Invertible domain one. Yeah, this is a thing we have an invertible domain one. So this is space. Yeah. Oh, oh, you want to say, oh, you have some movement. Maybe this is related to the spectrum, the idea of to like you have a continuous family of states belong to the same phase. You want to explore the topology of such state, right? No. Okay.
So basically, this is similar to your previous idea about annuals, that if we have a billion annuals, we can create a pair by a unitary operator. Then if we create many pairs in space, and two pairs, when they are very close, they could be annihilated locally, right? So my idea is to ask whether we could extend this process to invertible domain walls. We create many pairs of domain walls which could be annihilated locally.
Many pairs.
I think he's saying that if there exists this domain wall, do we directly know how to create this domain wall as a local unitary? But I understand what he's saying is that suppose I don't know how to create it, but I can at least start from a hole and move using these movements to move into it. Then I learn how to create that domain wall through testing how to deform the wave function across the domain wall. Suppose I am given this wave function, but I don't know how to create it. Then I learn it. That's how I understand what he did.
Yeah. So we only know this
So
single.
Given this wave function, you give me the wave function, but you didn't tell me how to create it from beta. But you give me the wave function where there's alpha and beta. Then I learn to create it by looking for ways to deform it every step, preserving A0 and A1, and learn that circuit. So I think he's doing what you're asking, except you want to learn that unitary operator directly from the wave function without knowing it in advance. I understand.
Yeah, thank you. That's it. Thank you for the interpretation. And right, so this one, we believe we almost have it. This is the grad student in contact. And this part, I believe we almost have this, but the answer currently, there seems to suggest this must be depend on the dimension on 2+1D. Maybe it's fine. We haven't checked all the details. But in 3+1D, maybe the same technique doesn't work. So we are still trying to understand what's going on here. Yeah, so there's some more puzzling. Okay.
So one possible definition for domain wall to be topological is that it can be moved or deformed freely, right?
Invertible domain wall.
No, I mean general domain walls.
General.
If we, I mean, there is not a precise definition of which domain walls are topological, right?
There are. Okay, let me define invertible. There are different ways to define invertible domain wall.
Yeah. I mean, before getting to technical details, I think the intuition is if something is topological, it must be freely deformed. Could be freely deformed, right?
Yeah, so invertible ones can be freely deformed.
I mean, even non-invertible ones. Otherwise, we cannot say it is in
well,
topological.
It can be deformed, but it's harder. It takes the linear depth circuit to deform. That's a theorem.
I see.
Yeah. Is there any questions? If not, I'm going to the last part of the A1 Pride, the overview of some fancy work of but some of my other collaborators. So I'm not involved, but I heard about them telling me all the time. So like a start about a circuit finance depth local unitary invariant formulation with the reference state on the ball still on the ball and A0 and A1 prime. By A1 prime, what they mean is that you draw similar figures for A1, but somehow this is a little bit fuzzy. And they require some fuzziness, and the way they do this is to introduce another region called D. C, E, and D. So it's like you have some definition reference called reference state on C, C, D, and E. And the condition A1 prime is to say that for any real A, B, C, D, E, yeah, you extend the state to including another region. Suppose such a state exists. For any such state, there exists a channel from BE to BC, such that when it acts on the ABE, give you the state rho ABC. Yeah. That one is slightly, well, it is strictly weaker than axiom A1. And once you have a circuit, so I told you about spurious contribution. What you do is that you just make the thickness of E to be large enough, then it turns out this axiom is still true. So it's a manifestly covariant formulation. Oh, by the way, I should say this is a Daniel Renan. As a PD, well, yeah, right. So this is a new formulation. If you really take this seriously and try to build everything, you need to reprove some theorems. Some are kind of a straightforward translation, but some are harder. And for example, this is the one version of the axiom. They were telling me that on a plane, they need to think about whether they need a reverse. Some yeah, what do I mean? Yeah, some reverse the version of this. So they believe that's not the independent axiom is trying to prove this follows from some other parts. And what makes a difference? So they can still define information convex set. And simplex theorem is okay. The two-hole disk, you have coherence, the fusion space dimension. Yeah, those are still there, but the tricky part is that the entropy difference is no longer conserved. That your A S of your A minus S of your 1. This still give you 2 log dA. Yeah, that's no longer guaranteed. And the topological entanglement entropy may not give you the correct answer. The modular commutator may not give you the chiral central charge. And if you really take this seriously, want to make everything circuit invariant, then there appear to be a lot of work to do, like how to define topological entropy and how to define chiral central charge. Yeah, especially the chiral central charge one. I think yeah, we don't know the answer yet. But on the you may ask whether this framework is the same with the framework based on A0 and A1. So that's the big puzzle. Well, some puzzle where you can ask it whether they give you the same classification of it. Equivalence or not. On this question, we don't know how to answer yet. For example, you can imagine maybe there exists. I suppose there exists a state satisfied A0 and A1 prime, but you cannot deform this to the entanglement bootstrap state with A0 and A1. Then perhaps the classification is different because one state with those set of axioms may not exist a fixed point with this one. But no one can find such a state so far. So we don't know whether they are equivalent, maybe they are equivalent. and under a special assumption, under the assumption that for each phase of matter, a gap phase has a fixed point, has a state with this fixed point of A0 and A1. However, we could show that there's a classification for the other universal property can be captured using this one without using that one. In other words, in this context, what the relation between the two frameworks would be like whether you want to use the rectangular frame or some frame with a different angle. You are free to make different choice of reference frame, but the end result that came out of this should be the same. And for the modular commutator there, there's I had an idea of a so-called soft invariant. On the third one, soft invariant. That's something is defined to be. Let me try to give a definition. It's some quantity, some fancy. Yeah, I came up with some letter. I don't know. M. It's computed from the box. That is not a finite depth, which is not a finite depth invariant. Finite depth local unitary invariant. Yeah, because some quantity that looks simple in this Cartesian coordinate will not be look as simple as this one, but nonetheless, I can show that the sense of soft invariant is that if you go from the entanglement bootstrap state to sigma 0 finite depth local unitary to another frame with A0 and A1. Yeah, it's more or less like a change of frame from this one to another one, but still with rectangle. And everything should be invariant. So if this thing computed from sigma 0 will be the same with that computed from sigma 1. I would call it a soft invariant, a soft circuit invariant. Yeah, I can argue that although gamma and J are not strictly finite depth local unitary invariant, but they are soft invariant. Yeah, the idea behind this is that soft invariant will be a more relaxed version, a weaker condition that guarantees something is the label of the phase of matter. So as long as you have there's a reference state with A0 and A1, you compute that quantity. You ask whether that's reliable or not. And if I can show that no matter which frame you choose that satisfy A0 and A1, you always get the same answer, then it's definitely a leap of the face of matter. So yeah, that's my kind of yeah, I was being lazy. If I'm lazy, don't want to draw some fancier partition, then we can still make progress using this philosophy, which is an alternative to this one. But there's a lot to develop on this one, and maybe if you have some solvable model, sometimes this axiom could be easier to check than the other one, or sometimes if you can find an example that's covered by this one, but has no fixed point with A0 and A1, we will all like to hear that. Yeah, that's the end of my talk. Thank you. Yeah, yeah, yeah. But it's a soft invariant. Yeah, it's like this right angle is not invariant, and the change of frame if you include this frame. Yeah. Yeah, but A1 is a trivial soft invariant. It always gives you 0. It doesn't help you to classify face of matter. But there are other more interesting weak invariant. One is the subleading term, gamma, which tell you the total number of anions. The other one is the modular commutator, which is supposed to tell you the chiral central charge. The, yeah. Yeah, it is an arbitrary FDLU, but with restriction that new state also satisfy A0 and A1. Yeah, this is non-trivial. If you wish, I can show a figure. Show a better figure illustrates what's going on. So it's like, suppose I have a set 0, which has A0 and A1. If you take an arbitrary FDLU, finite depth local unitary, you get to a state called set tilde. It has A0, A1 price, because A1 may be violated. But then you have a clean circuit, unitary, finite depth local unitary, that give you a state with A0 and A1. Again, it may not be the same state, so I call it a set 1. Yeah, it turns out there are quantities like modular commutator, the same here and there. It turns out I can show that J0 equal to J1, gamma 0 equal to gamma 1, although they may not be equal to that compute to on that state. Yeah, so that's a simple way to show that, oh, this formula is still useful for classifying face of matter. Question from the room. Yeah, if not, I think we can stop recording and people can ask more questions.它会自动录上。 也就是你知道怎么解释？